For our last example, we're going to look at a infinitely flat surface that has the charge distributed along the surface. And so one parameter that we need to define is sigma, which is equal to the charge divided by the area. And is evenly distributed along this surface. So we need to come up with a way of getting all the charges and integrating. So when we talk about a surface and we can look at it as a circle, the easiest way to do an integral is to start with a circle. So if I have a circle and I'm using the z-axis, well, I already know if I'm concentric around this this point where the z-axis goes through the surface, I already know the electric field due to a loop. And if I know that this loop is here and I know the electric field, this just becomes a differential electric field. So let's write down in terms of z the formula for a loop. So the electric field due to a loop, and we're going to translate to z to z-axis. And that formula is E equals 1 over 4 pi epsilon naught Q times X over square root X squared plus A squared cubed. So now I need to make a differential out of this loop. And so I'm going to have differential electric field. Well, let's look at what we can do for the electric field. Oh, and I forgot to translate this into Z. Apologize. Okay. And let's define this distance as R. Just changing some variables around here. Not a problem to do that. Okay, so R is a constant. Z will be a constant because it'll be some value that I specify. I say, okay, I want to know here. And I have constants at the beginning. The only thing I can do a differential is of Q. So I have 1 over 4 pi epsilon naught, and actually I can get rid of that 1 and I can put a Z out there. And I'm going to have dq square root of z squared plus r squared cubed. Alright, now I need to find my differential q. And that's just going to be, if I take a look at this formula, I would have, sorry, I'm marked on it. I would have Q is equal to sigma A, and Q, differential charge Q, is equal to, well, sigma is a constant, so I would have differential area. What do I use for differential area for a loop? Well, what I do is I take and make a little differential change in the radius. And if I cut this and string it out, if this was a rectangle, my drawing's not that great, well, this would just be differential radius, and the length would be equal to 2 pi r. That would be my differential area there. So different dq is going to be equal to sigma times 2 pi r dr. So let's write my differential electric field over here. Put everything in that I know. Need to put that as z. And now I have a differential in r, so this square root to the third power is going to have to be evaluated. And now I can do simplification and go for my electric field. Two pi is going to cancel out part of this 4 pi, and I'm going to get 2 epsilon naught in the denominator. Sigma is going to go, it's a constant, and I'm going to go from 0 to r. I can take r to infinity, and we will do that here in a minute. And I'm going to have r dr over, and that's square root z squared plus r squared cubed. Now I can evaluate my integral. And you can look this up in the integral tables. And this will be equal to, my notes here, minus 1 over square root z squared plus r squared the limits are going to be from r to 0. Now I can move the z in, and I will do that here in a minute. Let's just do so this is going to be minus, oh, I shouldn't have put an equal sign there. So if I put r in for little r, I get minus 1 over z squared plus r squared, and I don't have a square root, minus 1 over, and this is going to be, or I should say minus a minus, so that'll be a plus, and that will be 0 in for that, so it's going to be the square root of z squared. Because I put the 0 in for this r, z squared is, well, all that's left, and I can put that there. Now I can rearrange. I'm going to put z inside. And I'm going to rearrange. I'm going to flip these around here because I like the positive in the front. So I'm going to have z over z squared square root is just going to be z minus z over square root z squared plus r squared. And that's just going to simplify to sigma over 2 epsilon naught 1 minus z over square root z squared plus r squared. Okay. Well, what would happen if r squared was much larger, went to infinity? Well, if this goes to infinity, then this term goes away, and all I have is this value. So if r goes to infinity, then my electric field is equal to sigma over 2 times epsilon naught. Now let's look at what if z is approximately 0, very close to 0. Well, that means that this second term is going to cancel out, and I get that the electric field is equal to sigma over 2 epsilon naught. Well, that makes sense. If r is infinite, then I get this constant. If z is equal to 0, very close to 0, I get this constant, because the closer I am to the surface, let me draw this surface out. Let's say I'm right here. It's much, I mean, r, we'll say that this is r. R is so much bigger, it could be considered to be infinite compared to z being there. So it's as if you're looking at the same situation. If z is way out and r is infinite, it looks the same as if I put z really close to the surface and I have a limited circumference. Okay, that's another possibility. Now, what happens if z goes to infinity? Well, if z goes to infinity, then it's much greater than r squared. So r squared is going to go away, and I get z over z squared square root. Well, that's just going to be z over z, which is 1. 1 minus 1 is 0. So that means that the electric field disappears. And how can that be? Well, think about it that we're distributing the charge and over the surface, but we're so far away and the charge becomes so distributed along that surface that at infinity I really can't see it because of that spreading out of the charge. So, and that is why the electric field appears to go away when z is at infinity. So there's some interesting ideas. It's interesting to always take an equation, take it apart, analyze it, look at extremes. What does it tell you? Does it make sense? But this is the electric field at some distance z above a plate with a surface charge q.